Thank you for joining me on this talk. The aim of this is to give a quick fire round of best practices when developing edge AI. This gathers together some of what we've learned the hard way, hopefully giving someone new to this field a good starting point. The rest of this talk should be reasonably generic to all edge AI projects. For this talk, I will assume some familiarity with neural networks and embedded software. A quick introduction to Cambridge Consultants. We are a worldwide engineering consultancy with over 900 employees. We are headquartered in Cambridge in the UK, but have development labs and sales offices located in the US, Singapore, and Japan. As an organization, we help clients with tough engineering problems in a wide range of fields, including medical devices, robotics, wireless, defense, and AI. We are now part of Capgemini Invent, adding the capabilities of a larger team of 280,000, and we are also an ARM design partner and an ARM functional safety partner. And a quick intro from me. I'm principal engineer at Cambridge Consultants with a background in digital signal processing. Over the past 5 years, my research activity has largely been around the exciting field of edge AI. Before we dig into the best practices, I would like to first set the scene for an edge AI development by quickly showcasing a project we did recently in partnership with ARM. As a company, we work on projects with some of the world's biggest brands, but we also invest in our own research to advance technologies that are important for our clients in the future. It is one of these projects that I will present today. Our team came together to address one of the biggest healthcare challenges the world is facing today, tuberculosis. This is the second largest cause of death by infectious disease in the developing world. I'll show a concept system that shows how edge AI has the potential to come together to address this. Previously, Cambridge Consultants developed a neural network model to assist with the medical diagnosis of tuberculosis by counting bacillus bacteria in a slide. This used a relatively large unit that was deployed on the cloud, with a smartphone used as a front end. High-resolution microscope images were sent from the smartphone camera to the cloud for inference, and the results returned to the smartphone. The goal was to take this server-based deployment and port it to an edge environment. By not relying on the inference being run on the cloud, this would allow the system to operate where wireless connectivity is poor or non-existent. For this project, we use an early version of the Cortex M55 CPU and the Ethos U55 neural network accelerator on an FPGA development kit. We also wanted to integrate a camera and a display, making this a complete device. There were a number of tasks to complete with this project. This will be a whistle-stop tour of the process. The first was to bring the toolchain up. We then retrained and ported the neural network in the TensorFlow environment. This was then quantized using the Vela compiler to produce a model that could be run on the M55 and U55. The model was then deployed and debugged on the target hardware. Profiling was then used to guide further optimizations and improve performance. Once the model was running, we integrated the camera to capture slide images. And then finally, the whole system was wrapped up in a UI on the display. There's a photo to the right-hand side of the complete system. The results speak for themselves. We have cloud-sized machine learning running at the edge, consuming a fraction of the power and without the need for wireless connectivity. For each microscope field, 280 billion multiply accumulate operations are performed in just a few seconds. And with the U55 accelerator, we saw 7 times power reduction over just the M55 and a 1,000 times performance improvement. More details are available in the blog post at the bottom of this slide for those that are interested. So this should give a taste for what is involved in a real-world application of edge AI. And it should be clear from the previous example that using edge AI is not just about handling neural network models. There are lots of other factors that must be considered. This leads us on to the main part of the talk. This next section will present some insights into how to select and evaluate edge AI platforms by analyzing a project's goals. Performance comes in many flavors. If we take the example goal of this product should be the best mobile something, we can conjure up some requirements related to edge AI that would be relevant for this kind of product. This might be efficiency in tera operations per watt, throughput in tera operations per second, maximum power in watts, package size in millimeters squared, or performance per cost in tera operations per dollar. There might be further requirements on the system, such as needing various digital interfaces to sensors, for example. Edge AI platforms have a big range of different capabilities and limitations, so choosing an edge AI platform can be a complex task. It is thus necessary to identify these requirements that are really what gets us the product we need, so we can select a platform properly. This requirement capture stage is the ideal time to understand the size and type of neural network to be deployed if possible. This might be the number and type of layers, as well as the total number of operations. Once you have a basic list of requirements, it's a good idea to take stock of them. It's useful to get an idea of which requirements are strict, which are flexible, and which are difficult. Focusing on those which are strict and difficult first allows us to rule out unsuitable platforms early. Flexible requirements allow the designer to trade off different aspects of the design against each other. It is at this point worth noting that good requirements can lead the way to a solution that is good enough. While there are some incredibly impressive edge AI acceleration hardware out there, for some systems, the humble CPU is perfectly adequate and comes with advantages in terms of cost and ease of use. One further consideration when building a system is to ensure that it is future-proof. Sizing requirements for a sensible expansion in capabilities is generally advisable. If there is a possibility that the type of model may change in the future, this is a good time to find this out, because highly efficient acceleration hardware often has limited support for every type of neural network model. If requirements cannot be satisfied by off-the-shelf products, custom silicon is an option. Once a concrete set of requirements has been collected, the Edge AI platform must be selected. The huge variety of hardware and software offerings for Edge AI in the marketplace today means there often is a solution that will work, but the key question is which one to choose. Ideally, we want to rule out candidate platforms early and with the least time spent doing so. To do so, we have a few options in roughly ascending order of difficulty, matching key requirements up to datasheets, obtaining an evaluation kit to run software experiments, and finally doing hardware-based measurement of metrics such as power consumption. Running experiments with the device is often important for Edge AI. Lots of devices and tools are still in active development, and surprises can pop up from time to time. These may only be discovered by experimenting. Alongside this, datasheets and marketing materials may only give headline figures for the device. The actual performance with the target neural network can be a long way off these. Because power consumption is a complex function of what activity is happening on the device, it is valuable to measure this on the bench. Datasheets, again, will often just give nominal values for power consumption. These considerations are in some ways similar to those for typical embedded projects, but the sheer variety of platforms and the relatively immature state of this technology means that verifying performance is extremely important. Across a range of platforms we've used in the past, we have found quite a few surprises. For example, using a camera interface causes one of the CPU cores to be pegged at 100%. The type of neural network causes extremely low utilization of the acceleration hardware, less than 1% of the headline figure. Buggy software tools that seemingly crash at random, and acceleration hardware that can only support neural networks with a batch size of 1. So these just go to show that thorough evaluation is necessary when deciding on an Edge AI platform. I'll next move on to some points around tools and frameworks used for Edge AI and how they differ from more traditional neural network frameworks that might be found on the desktop or in the cloud. I will then discuss some of the techniques that we've been using to get the most out of these. A typical cloud-based deployment of a neural network might look something like the diagram to the left-hand side. A model in one of the popular frameworks is deployed to one or more computing nodes, and the cloud runtime executes the model on a CPU or a GPU. Often, the training framework matches the runtime. For example, the TensorFlow model is running inside the TensorFlow runtime. This integration means that there are rarely problems with compatibility between the model and the runtime environment, and the switch from training to inference can be just a configuration line change. Because this deployment usually runs inside Linux, the complete set of mature debugging and profiling tools can be used. Scaling this kind of deployment for greater performance can often mean just adding more compute nodes to the cloud. Tools like Docker and Kubernetes have made this relatively straightforward. In contrast to a cloud deployment, a typical edge deployment has some more parts and more things to be aware of. The diagram to the left shows a typical workflow for edge. The same industry standard models are input at the top of the workflow, but this is where the similarity stops. Usually the next step is a vendor-specific toolchain, which converts these standard models into something more specific to the target platform. Generally, and I would say currently, the flow through from TensorFlow models is best supported by most platforms. Using Onyx as a format for interchange from other frameworks is mostly supported, but there can be subtleties involved. Typically, deployment uses a reduced bit depth model, often 8 or 16 bits, but sometimes as low as 4, 2, or even 1 bit. When compared to the original Float32 model, this has implications for model accuracy that must be verified. Furthermore, a deployment that quantizes the model uses a calibration data set to determine how to scale each layer. This must be fed into the vendor toolchain alongside the model. The next blocks, marked in orange, exist on the target platform. The converted model is run within the edge runtime. Unlike the cloud deployment, this is usually not the same as the training environment. Sometimes this is a reduced feature set version of the full training environment, for example, TensorFlow and TensorFlow Lite, or it could be an entirely new environment, for example, the KPU runtime of the Kendra devices. The actual execution of the model is delegated to either the CPU or the hardware accelerator. Usually, Edge AI runtimes have a reduced set of supported layers when compared to cloud-based runtimes. Often this is limited to convolutional and fully connected nets, and sometimes RNNs and LSTMs. Where this often trips people up is with the convenience layers available in larger networks, such as JPEG decoders or FFTs. Usually these will not convert into a model for running at the edge. One thing to be aware of are some silent incompatibilities when using edge frameworks. To debug, for example, conversions between neural network models such as Onyx to TensorFlow can end up being functionally correct, but with very non-optimal layers impacting performance. Once a platform and a framework have been selected, we move on to verifying, debugging, and fixing problems that we might encounter when using these. We'll start with verification. Verification is an essential part of every Edge AI deployment. Verification should be an ongoing process throughout the project rather than just at the end. End-to-end verification of the model's functionality is critical to ensure that once the model has been deployed, its accuracy still meets the requirements. The verification must be set up to demonstrate that all of the pieces of software and hardware, from sensor inputs to results, maintain the accuracy requirements set out at the start of the project. Critically important here is that the accuracy of the deployed neural network is measured by including all of the data pre-processing and post-processing blocks too. Just like any other good software project, unit testing and continuous integration are essential. Where possible, it's useful to have both simulated continuous integration as well as hardware-based continuous integration. Simulated CI has the benefit of being able to scale the size and number of tests almost infinitely and is often easier to set up and debug. On the other hand, hardware CI provides a much greater confidence in the accuracy of the results, can test hardware peripherals such as sensor or radio interfaces, and can collect accurate measurements of clock cycles. This last point brings us on to an important step with any embedded project. The real-time requirements must be understood and met. This verification should be done with all of the software systems exercised and not just the neural network model itself. Power is often a key requirement for edge deployments. Measuring the power consumed by the device should be done on hardware with a full suite of software to be run in all of its operating modes. It's worth emphasizing at this point, all of these verification steps should align with the requirements. Now, moving on to debugging. Let's say that our verification shows that we are not meeting one or more requirements. The following are a few techniques that we have found useful. Performance bugs can be tackled with tracing and profiling tools. These are often included in the runtime environment or as part of the hardware vendor's SDK. One important factor when debugging performance is to thoroughly understand the memory hierarchy of the system. Neural networks are extremely bandwidth sensitive, so careful attention must be given to where data is stored. One of the challenges with Edge AI runtimes is that debugging issues when using hardware acceleration can be a little trickier than with just software. There is often limited visibility into what the hardware accelerator is doing. You can't just attach a debugger to these. Ideally, the hardware vendor supplies tracing tools to inspect the state of the hardware, but these aren't always available. So how do we get around this? Generally, the first step when debugging a neural network is to identify which layer or group of layers are causing problems. And the following two techniques have proved useful to us in the past. The first is bisecting a model into two parts and running just the first part on the hardware. The output of this truncated network can be compared against the reference model in the original framework. Sliding the point where the model is split along the depth of the network and rerunning can pinpoint where the two diverge without having direct visibility of what is happening inside the hardware. A second technique is useful in tracking down inaccuracies when using quantized models. And again, there is limited visibility inside the hardware. By selectively quantizing only some layers and running the network, the reduction on the network's accuracy can be found. Changing which layers are quantized and which are not gives an indication of which are the most sensitive to quantization. So, what mitigations can we do to fix a problem that doesn't meet the requirements? If accuracy is poor, this can often be caused by bad quantization. This can be the trickiest part of a successful deployment. As mentioned previously, quantization needs a calibration data set to work properly. One common pitfall is not to supply enough of the right kind of data. I could fill a whole second presentation with pitfalls around this area, but the key things to remember are calibration data should contain at least a few hundred samples, and it should be the same shape and data type as the reference model. If quantization is not to blame and accuracy is still poor, sometimes the number of bits used for inference can be increased. If performance is poor, one important step is to ensure that the device's memory is set up correctly. This could be moving critical data into faster sections of memory or enabling caches and prefetch units. As mentioned before, not all frameworks support all layer types. If your network does contain unsupported layers, there are a few options. The first is the most direct route, just hack the framework to add the layer. The common frameworks are all open source, and this can be a viable option, but with a bit of a steep learning curve for newcomers. The second option is to change the architecture of the network. The problem may be solved with a type of network that is better supported. A third option is to feedback a request to vendors to support your network type. We've found that both proprietary and open source vendors have been very welcoming of feedback about what people want to use their platforms for. Alongside this, the TensorFlow Lite Micro SIG is a particularly active and a great way to learn about where this project is going and request new features. Now, this might all sound like a lot to worry about, but the good news is that tools and frameworks have been improving rapidly over the last few years. Usability, compatibility, and performance are getting better every day. And there is a steady development of new tools that integrate a lot of these individual pieces into low code, no code, or AutoML products. These can provide a much faster time to market where the platforms or models in mind are supported. The final section I want to talk about is model management. Once a neural network is ready for deployment, how do we do so effectively and securely? Perhaps more so than cloud deployments, edge deployments need careful management. The next slide introduces some of these considerations. For many deployments, the neural network can often be the largest use of storage on a device. To give an indication of scale, we have recently deployed a model to production weighing in at 64 kilobytes on a device with just 128 kilobytes of flash memory. In embedded devices, accessing data such as neural network models stored in flash instead of static RAM usually comes with a performance and energy penalty. However, the trade-off is that the cost of flash is a lot lower. For larger devices with dynamic RAM, a similar trade-off can be applied between dynamic RAM and static RAM. One useful trick to maintain good accuracy while limiting the size of the model that must be stored is to take advantage of hybrid models. These have a lower bit depth for weight storage than activations, for example, 8-bit weights with 16-bit activations. These have been supported in ARM CMSIS NN library for a long time and are now making their way into higher level libraries such as TensorFlow Lite Micro. Additionally, weight compression where available is also very effective at reducing model size. And changing the type of model from traditional convolution to depth-wise convolution can be quite effective at reducing the model size too. This speaks to a larger point that changing the architecture of the model in order to fit the constraints of an edge deployment is worth exploring. This exploration is made much more effective by strong end-to-end continuous integration to quickly verify how changes in architecture impact accuracy. Security must also be considered when deploying to the edge. Generally, any sensitive code, data, or models should be encrypted, and the data transferred via radio must also be encrypted. But as with all secure devices, a threat analysis must be undertaken to properly construct the security architecture of the deployment. Deployed devices often need management once they're out in the field. One common functionality is over-the-air updates to upgrade the software and models on the device. Often there's limited communication bandwidth to the device, so how and when to do updates should be considered. System monitoring is useful once devices are deployed. Understanding the health of the units already in the field and collecting usage patterns can guide more effective deployment. Sometimes it's also useful to provide a mechanism to collect raw sensor data that can be aggregated to improve the training of future models. Again, there's lots of things to think about with model management, but new tools and new environments are making this easier every day. And so to quickly wrap up this talk, Edge AI brings new opportunities and new challenges requiring new solutions. Unlike traditional neural network deployments, Edge AI has additional considerations around power budgets, real-time targets, accuracy, integration, and deployment. However, the market is responding with new solutions. More capable neural network acceleration IP, such as the Ethos U55, allow massive leaps in performance, and the software supporting this new hardware is also continuously improving. Moreover, there's a plethora of new applications that vendors now support out of the box, making it quicker and easier to innovate. Our focus has been to help clients transform markets by making AI run smaller, faster, and cheaper. We've worked at all levels of the Edge AI ecosystem, from whole system design through model development and training, building applications on a wide variety of platforms, building and extending tools, deployment, as well as developing and integrating silicon IP. So we truly roll up our sleeves and work at all levels of the ecosystem. So at last, I would like to say thank you for listening to my talk. I hope it's been interesting, and please do get in contact if you have any queries or comments. This paper talks more in depth about the technologies and strategies that can help bring more intelligence to edge devices. This is available from our website at the link at the bottom of the slide.